the concept of vector relationships. So we're going to be looking at two vectors and how they compare to one another. Okay, and we're going to talk about it in terms of leading and lagging. Okay, so that's how we refer to the relationship between a couple of vectors. Okay, let's take a step back for a minute and remember that we're going to be using vectors to represent an AC waveform. Okay, so there's a sine wave representing a particular voltage or current, and we'll call this waveform A. And then I'm going to draw a waveform B, and I'm going to try to shift it. So we call this a phase shift. We've talked about this in three phase, that the phase shift is 120 degrees. I'm going to try and make this 90 degrees, which means the sine wave, the waveform, is going to begin at 90 degrees. Like that. So that's waveform B. Okay? So this is voltage A and voltage B. Let's call them voltages. Okay? And now what we're going to do is we're going to take those two waveforms, and I made the magnitudes different on purpose as well. That's not really the point of this conversation. Magnitudes don't matter here. We're talking about the phase shift, but just to throw that in there as well. So let's graph a couple of vectors that are going to represent these two waveforms. So first thing I want to underline is the fact that the horizontal plane to the right is our starting point. Okay, we're going to call this 0 degrees. Okay, so that's always going to be our 0 degrees. That's our reference point. That's where we begin. Okay, from there we're going to rotate in a counterclockwise direction. So that is forward rotation. Okay, which means this is 90 degrees, this is 180 degrees, and this is 270 degrees. Okay, so the first thing I want to do is I want to draw a vector that represents waveform A. Okay, and honestly, in terms of the direction of this first vector, I can start anywhere. Okay, makes sense to start at the beginning. We started the waveform at 0. Let's start the vector at 0. Okay, so let's say that vector A, which represents waveform A, has a direction of 0 degrees and a particular magnitude. Okay, that is vector A, representing waveform A. Now, waveform B is delayed. Okay, so it starts its sine wave 90 degrees after A does. And so I'm going to draw vector B lagging vector A by 90 degrees. So if this is forward direction, lagging behind means that vector B is going to be down there. Okay? So there's a 90-degree phase shift between vector A and vector B. And B is said to be leading A. Okay? So let's eliminate the sine waves because we're done with the waveforms. Okay? Everything now is going to be about the vectors. Okay, so let's look at our two vectors. Okay, there's vector A and vector B. In fact, I think I want to... Shall we start over? Let's start over. That's a really good conversation. That's an introduction to help us recognize what it is we're talking about, right? We're using vectors because they're nice and simple. Okay, it's a straight line with magnitude and direction representing the much more complicated sine wave. So, let's draw our grid, 0 degrees, 90 degrees, 180 degrees, and 270 degrees. And let's use blue. Let's call that vector A with the direction of 50 degrees. Now let's draw over here. Let's put it right there. This is vector B and it is at an angle of 110 degrees. Okay, so there's our two vectors. We've plotted them. We don't know the magnitude. That's okay. We're not too concerned about it. It's the direction we're interested in. Vector A is at 50 degrees. Vector B is at 110 degrees. Okay, we can now make statements about the leading and lagging relationships between these two vectors. Okay, so the first statement I would like to make is that B leads A. By how much? Okay, remember that this is forward direction. Okay, so that this is a racetrack. This is the start finish, and this is the start finish line. Okay, and we're running around the track. All right, B is winning the race. Okay, B is ahead of A. B leads A by how much? 110 degrees minus 50 degrees. B leads A by 60 degrees. Okay, so that would be a true statement about the relationship between these two vectors. Okay, but not the only true statement. We could also say that A lags B by how much? This is the race. B's winning. A's losing. A lags behind B by how much? That same 60 degrees. Okay, so those are the two statements that are fairly obvious, but they are not the only true statements that we can make. There are actually two more. Okay, if this is a very long race and we're going around the track many times, okay, and in fact remember that these vectors will go around the track from 0 degrees all the way to 360, okay, in a single sine wave. And remember that in North America, the frequency of our AC power supply is 60 hertz, which means the vectors make a lap of that track 60 times every second. So this is a really long race and they're running really fast. So while it looks like B is leading A, it may be true that A is actually catching up to B and about to lap him. Okay, and so perhaps the difference between the two vectors is not this 60 degrees right here. Perhaps the actual angle of interest is from here all the way around to there, which is 300 degrees. And so while these statements are true, there are two more that are also true, because it may be said that A leads B by how much? A is ahead of B. If we look backwards around the track, how far is A ahead of B? It's ahead by 300 degrees. So we could say that A leads B by 300 degrees. And finally, one last statement, we could say that B lags A by 300 degrees. Okay, so there are four different ways that we can state the vector relationship, the leading and lagging relationship between two vectors when we plot them like this. Okay, so that concept is going to become really important as we move forward. Okay, when we get back into actual electrical circuits and we try to understand the exact nature of the circuit, this idea of phase shifting and leading and lagging will be central to the work that we do.